Lunch Seminar in 2019. We started another fantastic year of talks. So the first one is by Lia about computer vision and machine learning. Thanks a lot.
Thank you. I will try to speak without the microphone, if you can hear me, so I have my hands free. But if at any time you have trouble understanding me, just stop me and I will take back the microphone. Thank you for the introduction, thank you for coming. Such a great number. I would like to start just by giving you a few information about myself, about my background. I got my PhD here at Polytechnico. A few years ago, 2006. And for many years I worked in a company, IM3, which was at the time a startup based in Turin. And my focus of research was mostly medical image interpretation and screening. So how can we teach computers to detect early signs of cancers in radiological images before they grow and become symptomatic? And from a few years, I had the opportunity to lead a multidisciplinary research team that focused on the intersection between pattern recognition, biostatistics, and human-machine interaction. So, on one hand, how can we detect early signs of cancers, but also how deploying machine learning in a clinical setting can affect the diagnostic process of the radiologist and the cognitive process that goes behind the human interpretation of images, but also population health. What is the impact on the global population health? And last year I joined the BRAINS group, the Graphics and Intelligent Systems, here at Polytechnico, with the focus on computer vision and machine learning. So today, what I would like to give is my own personal perspective on what is the state of the art in computer vision, present a few case studies from some recent projects that we are starting here at Polytechnico, and of course give my personal interpretation of what avenues of future research could be particularly interesting in the upcoming years. As probably many of you already know, deep learning is the main tool that we now have in computer vision. And the main difference between deep learning and with previous approaches to pattern recognition is the opportunity of learning feature extraction. So before the introduction of the convolutional neural networks, pattern recognition was also based on machine learning. We don't have to forget that machine learning has always been in pattern recognition, even before deep learning was available. But most of the work was actually through feature engineering. Whereas now we have the opportunity of training the features, the representation, and the classification within the same system through backpropagation. The main tool to learn feature structure for images are the convolutional neural network, and as the name implies, what they do is they learn basically convolutional filters. The advantage of using convolutional neural network is that we can exploit a little bit of prior information about the properties of images, in particular stationarity and locality. So the features that we use in one part of the images are translated across the entire image to obtain several features representation. And the third property that we exploit is compositionality. So features that are learned at early, so we stack layer of convolutional layers one on top of each other, and the features that are learned at the early layers are very simple, basically lines and blobs of colors. And they are composed on increasingly complex features until we can detect objects such as, for example, the parts of a car, of a vehicle, or the head of a board, and so forth. And based on these features, we do the classification. And we have now very complex models, but the main approach that was actually discovered in 1996, the first paper on convolutional neural network was published many years ago, was basically based on stacking convolutional layers and pooling, which basically just does a complex feature representation. Since what we have today that makes this approach feasible, which we didn't have in 1996. Three main ingredients. The first ingredient is data. We have data sets that are very large scale and are such as ImageNet, which is the first and most famous, but we also have other data sets that, for example, for place classification, we have now visual genome, we have now taxonomy, we have a number of large-scale data sets that we can use to learn various types of representations. Computing power, GPUs are now in great demand for this, especially for computer vision where the input space is multidimensional. Computing power is essential. And the third ingredient is engineering. To be able to scale from AlexNet, which was the first successful attempt at computer vision, to the models that we have nowadays, which are hundreds of layers and hundreds of millions of parameters, we need a lot of engineering tricks that were discovered during the years. So kudos to engineers for this one. What is, to me, one of the most interesting aspects of deep learning is that they provide a unifying perspective for all perceptual problems. Because although there are differences between the different models that we use, we can basically use the same tool for text, for visual representation, for speech, for audio, or as I borrowed from a conference that I attended, we have one perceptron to them all. Although, in my opinion, the perceptron has a much brighter future ahead than this range. And it also was a very unifying perspective from different fields. I come from a different field, which is medical image interpretation. And for 8 years, medical image interpretation and computer vision were two separate silos. They rarely talk to each other. We had separate conferences, separate techniques, separate feature engineering, and it took a while before the medical field took up deep learning, but now it's becoming the mainstream approach also in the medical field. And even radiologists, these are pictures from the main radiological conference in the United States, even radiologists are picking up machine learning and attending deep learning courses. So it's not just the computer scientists that are interested in these kind of technologies. Let's see an example. One of my field of application is mammography. Mammography has been for many years one of the holy grails of computer-aided diagnosis. Because, for instance, it has a high relevance from a societal point of view. Many women die of breast cancer, and it could be prevented. It also has a high potential for automating diagnosis, because screening mammography is a very standardized workflow. We always have the same images, we have very repetitive work, and it's very cognitive demanding for the radiologist, who is basically left looking for a classical needle in a haystack. But it's also a very challenging machine learning problem, because the patterns that we're looking at are very subtle, they are very diversified, and they're very rare. And I'm saying here for cancer, every 1,000 screening cases, But if we look, for example, of micro-classification clusters, which are these tiny white dots, these type of cancer is much rarer than that. And we also have very limited data compared to ImageNet or the very large data sets that I was mentioning before. Luckily for us, the representations that are learned by convolutional neural network are highly transferable. So we can take a network that was trained on ImageNet on a source task for which we have a lot of data, and even if this source task is very different from the task that we have here, this doesn't look anything like a photograph would do. We still are able to initialize our neural network with what we have learned on ImageNet and obtain way better results than just training the images on our model. But the target text that we have had a very limited data set. We had less than 100 micro-classification clusters. Although it took years to collect the data set, the number of lesions that we have is still very small. So we couldn't directly fine-tune on this target test, and we used a bridge data set, something that is closer to the target test, which is screen field mammography, but less, but still not as different as the source test. And we use convolutional neural network as feature extractor, but then we use statistical machine learning, which has random forest to train the final classifier. So here is a look at the type of patterns that what we're trying to do is we are trying to discriminate these classification clusters from the normal cases. And for this bridge data set, we had a sufficient number of examples to actually train the representation. And the beautiful thing is that not only we were able to train representation from very large networks that have millions, tens of hundreds of millions of parameters, but that the largest network are the ones that actually can generalize better to the target domain, because the representation that they learn are much richer in the type of features and the number of features than the smaller networks such as SqueezeNet that have very limited number of layers. However, computer vision is not only classification. There are many other things that we want to be able to do with our networks. And with this same tool, there are many tasks that we can solve. The standard example that we see for convolutional neural network is classification. So we have one image, we have a number of classes, and we just want to assign the input image to the correct class. But for example, one other task that we would like to do is object detection. So we don't want to just tell whether there's a car in the image or a person in the image, but we also want to detect where. We would like to do segmentation. So we would like to detect the boundaries of each object. We would like to be able to produce captions. We would like to be able to analyze not just images, but also videos. And for example, we would like to be able to generate new examples. These are examples of faces that have been dreamed or hallucinated by a generative adversarial network. And many more. We could probably spend the entire afternoon in going through all the models that have been published in the literature in the last few years. I think that to understand the type of models that we have, we could start by looking at the autoencoder. The autoencoder was initially proposed to do unsupervised learning. So we have an input space, and we want to compress it into a latent space representation. And we want this representation to be, of course, much more compact than the input space. But we also want it to be rich enough so that we are able to reconstruct the image from the initial, from this latent space representation. This model by itself is not as used as it was a few years ago, because most of at the state of the art, most of the networks that we see are actually learned through supervised learning. So we train by providing example of the input and the output space. But the very clever idea was to use the same architecture, but not try to reconstruct the original image, but we can try to reconstruct another image. So for example, the output segmentation. So we can use this same architecture to bridge two spaces. One input space, which is the RGB space that we are usually encoding images into, and the target space, which, for example, in this case is segmentation. But we can do the same thing for any number of applications. For example, we can go back from the labels to imagining the street, the initial scene. We can, for example, take images that were in black and white and apply color. We could perform day to night. We can go from sketches to photos and vice versa by employing this encoding and decoding. So I'm encoding in the feature space, and I'm decoding in another space from that bottleneck representation. The decoding doesn't have to be in the same visual space. We could, for example, use the same concept to decode using a language-generated neural network, which will not be a convolutional neural network, granted, but it can learn the statistical association between words and the corresponding images. So we can learn to associate the word people to the image of peoples just by looking at the examples of pictures and captions that were given by humans, using a data set that is sufficiently large to be able to learn these statistical associations. One of the beautiful things of all these networks is that they learn different representations. The representations that I need for classification are perhaps different than the representation that I need to do segmentation. But these representations are closely connected. This is a picture from Silvio Savarese's lab taxonomy paper, and they have taken a large number of different tasks. We see here 26 different tasks that are useful in computer vision, and they have computed the closeness of the representations that are learned by learning different tasks. So we know that if we want, for example, to compute occlusion edges, this task is very related to the task of computing normals, and we can exploit this similarity combined with transfer and multitask learning to reduce the amount of data that we need to use to train successfully and to obtain better results. Another problem that has been successfully tackled using deep learning is retrieval. In content-based image retrieval, what we would like to do is taking a large set of images. Well, this is not very large, but it's an example, of course. Take a query image and try to find if we have a corresponding image or a similar image in the initial collection. To do that, we cannot work in the initial space for two reasons. One is that images are very large, so this would be highly unpractical from a computational point of view. The second reason is that we can have images that have basically the same histogram, but they represent totally different things. So we need to work in a feature space which encodes the semantic and the similarity of the images. And once we have constructed this feature space, we can query it using a similarity metric, for example, Euclidean distance, but we can use any similarity metric that we want. We approach this problem from a very specialized application, which is duplicate detection, that I will show you a few examples in a couple of minutes. To solve this problem, we can use convolutional neural network as feature extraction. Here we see an image of a beautiful sandwich in Malaysia, and we have taken the last layer, the last convolutional layer of the standard convolutional neural network, and here are the activations that we see. And the beautiful thing is that these activations correspond to certain objects. For example, we have a sea, we have a trees, we have a beach, and we can use these features as a very compact representation of the image content and use these features to extract our feature vectors for query. Of course, the trained images the trained network that we have nowadays are mostly trained for classification. This is the main application, one of the most common applications. We have very large data sets. We have a number of networks that have been pre-trained on these data sets. And this is probably the first thing that we can think of when we do feature extraction. But the features that are run for classification might not be optimal for ranking similarity. When we try to learn good features for classification, we try to learn features that are very invariant to the different characteristics that a certain object can have. So if I want to recognize a chair, I want to be able to recognize a chair regardless of whether the chair is blue, red, whether it's a large chair or a small chair or a modern chair or an antique chair. But if I want to encode similarity, I need to do something that is a little bit more fine-grained than that. And one way we can do this is with Siamese network. Siamese network are a special case or a dual string network where the weights are shared between the two or free. We could use more than two strings, but for the sake of simplicity, we look only at the two string cases. So these two features, these two convolutional backbones, they compute the same features, and we train the network in order to map the input space to a feature vector or an embedding such that the distance in the latent space is approximates visual similarity. So basically, we want to take images that are quite close to each other and have them vectors that are very close in the feature space. When we use this network, of course, we can use only the top layer to compute the feature vectors. We don't have to use both streams. In this project, we had the opportunity to work with an insurance company, and their goal was to detect images that represent the same scene. And this is quite, and when I approached this problem, I was like, it seemed to me like a relatively easy problem. It should be relatively easy to say whether a room is the same room in different pictures. It turns out it's more complicated than that. For example, here we see example of pictures of the same room that have been taken with different orientations, with croppings. And here we see two pictures of different buildings. Those are different buildings, but since they were taken with exactly the same angle and the same orientation, they look like the same. You have to pay attention to see that they are actually different buildings. And it turns out that this is true for in many cases. For example, bathrooms. Most people's bathrooms look the same, especially if we look at the 60s architecture in Italy. Most images of bathrooms and outdoor pictures, they look the same. In this particular case, we had a lot of examples of damaged walls, and all damaged walls, they look the same to me. It's very hard to tell them apart. Whereas in some cases, when we do have the same location, it looks quite different depending on whether on the orientation we should take the picture. So it's more challenging than it looks. The other challenge is that when we do unsupervised near duplicate detection, we want to find all the near duplicates that we have, but we also want to find only the near duplicates. We don't want to detect false alarms. And most of the public benchmarks that we have, they look at basically the performance that you have when you try to find a query image in a collection and you want to retrieve similar images. But very rarely we ask the question, what happens when there is nothing to find? Can you actually say that there is nothing to find? And if we have a large data set, I'm saying here 1 million images, but nowadays 1 million images, I'm not even sure it would qualify as a large data set to many people. They would say probably it's a medium-sized data set. You need to do it with a false positive, with a very low false positive rate, because if my probability of finding a false positive is 1 in a million and I have 1 million image, I'm guaranteed to find at least one false positive for every query. So I need to go much lower than that to have a useful system. And one of the problems that we are facing with this project is that we didn't have any public benchmarks to compare with in terms of performance, or at least I couldn't find one. And so we have taken a collection, which is a very large, relatively large collection, and we are trying to find, doing a semi-automatic discovery to find all the non-identical, all the near duplicates. This entails looking at hundreds of photos of cats, because it's the internet and people don't usually upload these kind of pictures, to find the ones that actually depict the same cat and not different cats. With this benchmark, we can have relevant pairs. We can find irrelevant pairs that are very, very close, but we're not looking at all the possible pairs. That would be an infinite number of potential combinations. We're just looking at the ones that look very much the same. So we have sunsets, flowers, cats, all the type of images that people upload on the internet, and that in many cases people tend to take the same pictures with the same orientation, the same structure. And we can use these two set of pairs to compare their relative distance, and we're using this technique to basically recompare all the possible techniques that have been published in literatures to establish whether they have a performance that is high enough to be unsupervised in action. As we can see in the literature, in the news, in the media, there are hundreds of different applications that have been solved quite successfully with deep learning. But there also have been some spectacular fails. For example, in 2015 at the CVPR, a paper was published that found images that looked like nothing to us, but the networks could classify with a very high probability two classes, two classes. For example, they found networks that believe that this pattern was a starfish, or networks that look at these patterns and saw a peacock. And this is something that we as humans would never do. This is something very far from our way of seeing images. On one hand, we have tons of applications where neural networks perform very well, and in some cases they perform even better than humans. On the other hand, we have these spectacular fails. And what are the challenges that we are facing? And here I collected some of the most common objections to deep learning. And I think many of us agree or disagree to some extent with these challenges. This is, of course, my point of view, so I'm happy to take to be challenged on these. The first challenge is that the models that we have are very specialized. They solve very narrow problems. So when you take data that is outside the domain in which the network was trained, or you try to do slightly different things, they may fail unexpectedly. We are still far from the generalizability of human vision. The second point, the second limitation, is that they require a lot of training data. And this is somehow, in some respect, this is not necessarily true, because we can actually train models with very small data sets. If we use transfer learning or multitask learning, we have been able to use deep learning effectively even on small data sets. But to learn a new task, to learn very complex function, for example, for neural translation, we need very large data sets. We don't, at the state of the art, it's very difficult to generalize a new concept. It's still an open a research issue. It requires massive computational resources. I think this is a very crucial point. It's also a crucial point from an economic point of view, because it favors large enterprises, it favors large groups with the possibility of deploying a large amount of GPUs. So for smaller groups, or groups that are trying to get into the business of deep learning, it is a significant barrier. And I think it's also a problem for countries like Italy, where industry is mostly small, medium enterprises, and and we are and may not be willing to invest the computing resources that are required. And of course we have Amazon, but Amazon is not free, so you still have to pay. One thing that I think is also that CompNets have limited expressive power, and it's actually not very, may not be the most proper terminology. But what I mean is that CompNets actually make very little assumption about how images are made. Many of the properties that we take for granted, like for example invariance to scale, invariance to rotations, are not a property of convolutional network. They are learned from the data. They are a property of the data. And in other types of structural relations, such for example, the spatial relationship may not be easily encoded in CompNets, especially due to the pooling operation, which is very simple. It is in most cases very effective, but it's also a very crude way of putting together layers at different hierarchical levels. So, for example, a couple of years ago, when the capsule network paper was published by Hinton, it was designed to solve the limitation of pooling layers in convolutional network. But at the present time, the algorithms that we have that can scale to large data sets for training are mostly based on not entirely based on just on pooling layers and convolutional layers, but mostly. Deep learning is a black box. I partially agree with that in the sense that although we don't have a precise mathematical formulation of why deep learning works the way it works, we have a number of ways of poking our systems to understand what is going on. Can do population studies, sensitivity analysis, visualization techniques that help us understand what is going on. So I don't think that they are entirely a black box approach, but it's certainly not an intuitive interface between the convolutional network and the end user to understand what is going on. And one challenge that we also have is that they tend to overfit biases in the data sets. And by that, I don't necessarily mean societal biases, but any patterns that is due to the selection of a data set and not to the properties of to the actual properties of the images can be picked up by neural networks, because neural networks will just look at statistical associations. And I think this is also a challenge from the point of view of the research community, because most of our research is basically based on benchmarks, on publishing incremental increases in performance on the same benchmarks over and over again. And this can lead us, as a community, it can lead to overfitting with the benchmarks that we are using. So my humble suggestion, one of the things that I think are particularly interesting in the years to come is how to better integrate representation learning with reasoning. There has been a strong interest in combining machine learning, which is very good for perception. It's the best tool that we have now for perception, with statistical reasoning and knowledge representation. And at the recent symposium, there was an interesting contribution by Frank van Hellemond that tried to categorize all the efforts that have been published in the literature using these 3 or 4 blocks. data and machine learning, which is the state of the art, so learning from data and trying to produce other data, which are usually labels or text, and using symbolic representation and inference. One way that we can combine this pattern is to use machine learning to bridge from data to a symbolic representation, and then use reasoning over that symbolic representation to produce other patterns. So, for example, we can use machine learning to detect objects and then reason over the properties of those objects using knowledge representation and reasoning. Another approach is to use machine learning sort of black box approach, and then use another machine learning system to try and learn a retrospective symbolic explanation of the predictions that are produced by the system. This is also something that has been attempted in literature in the last years. Another way we can compound this Lego building block is to use symbolic representation as a prior for machine learning over data. And to do this for a convolutional neural network, we have to somehow encode our symbols in the network so that we can then use backpropagation to refine this symbolic prior over the data that we actually observe. There are many ways that we can use, many tools that we can use. For example, one tool is logic tensor networks, but I think that the main point is that a relation between two symbols can be represented as a function between tensors, and that can help us bridge these two representations. So if we think this as a model for semantic interpretation, we can think of systems that we don't have yet, of course, that can work at two levels. One would be the neural space, and one would be the symbolic space. And we can use neural symbolic integration to bridge between these two spaces. What are the advantages? The advantage could be that the system is much more modular, so we can separate different functions. We have smaller components that are easier to train, require probably less data, and we have a symbolic space that we as humans can understand, can manipulate, can use for reasoning. We can use it to import prior external knowledge and guide the learning process. One of the reasons why humans are much faster at learning is that we have a number of biases and we use a number of prior assumptions about the world than machine learning systems don't have. This is an example that was published at NIPS by the group of George Tannebaum. And they use this approach for solving a very specific problem, which is visual query answering, and in particular, they use it for solving the CLEVER challenge. The CLEVER dataset is a synthetic dataset. It was generated using rendering, and it entails answering questions such as like, how many cubes that are behind the cylinder are large? To solve these type of questions, we need to use reasoning. We can, in principle, learn it from a set of answers and pairs. So we can use a completely neural deep learning system to learn a function that, given the query and given the image, tries to predict the answer. This is absolutely possible, and it has been done in literature. What they do here is differently is that they use deep learning to extract a symbolic a structural representation of the scene, and they use another piece of another neural network to learn to encode the question into a program, a symbolic program. And when we have these two elements, we can then use reasoning. So, for example, if this program can filter the scene by shape. So it can take this structural representation and extract all the elements that are a cylinder. Or it can encode spatial relationships. Neural networks are not very good at detecting whether an object is up or down. They don't encode very well the relative position of objects, whereas we can do it symbolically very easily. And for example, we can count. Counting is something that is very easy to do when we have a symbolic representation, but it's very difficult to do in a pure neural approach. So to conclude, I think that we can all agree that deep learning is a very powerful tool that if we have a very specialized task, it can work very, very well. There are also been many exciting developments that we simply cannot fit into one lunch seminar, so we will need other lunch seminars to come and cover other developments such as multitask learning, adversarial training, attention memory. All these advances are actually producing elements and networks that are much more powerful than standard convolutional neural network for classification. But at the end of the day, I think that solving vision requires perceptioning, it requires reasoning, and it requires imagination, the capability of imagining things, of making prediction about the world that we observe. This is not just, of course, computer vision is artificial intelligence as a whole is facing this challenge. So thank you for coming, and I'd be happy to take any questions. Thank you. Thank you for breaking the ice.
Thank you for this very nice overview of the field. I start from this last phrase, the statement that you make. Vision is more than perception. And then you list here perception, reasoning, imagination. One thing, I mean, you were very much focused on 2D vision, so images. One reason why, when you say vision is more than perception, that resonates a lot to me, because I spent half of my life on images and half of my life with robots. And of course, for a robot, vision is the entry point that has to support reasoning and anticipation, etc., etc. So, can you say anything about all that part of work that is dealing, for instance, with depth information, with 3D point clouds? Because my very first thing is more than perception, yeah, because I have 2 eyes. And even just that, so even if when I see an image, actually I do remember a sense of depth, so I look out of the window and I see the mountains and I know they're far away, even from a 2D image. So can you say anything about that?
Yes, sure. I come from the world of 2D images, or 3D, but for medical image, 3D and 4D means totally different thing there for the computer vision, and certainly for robots that even more important. One of the I think my talk was very much focused on interpreting images from a 2D perspective. On that, I agree with you. That vision in the robotic field means of course a lot has to do with the sensing the world as a three-dimensional problem. And in that respect, for example, one of the things we can go back. One of the advantages of this encoding and decoding structure is that we can, for example, try to ensure also the depth of the object. We can use this opportunity to the same structure to learn many different tasks that are related to inferring the three-dimensional structure of the world from the 2D images that we present. For example, that estimation, many ego motion, the sense that we are in a certain place, and estimating our position from the external world. With that respect, I think that having a model that can learn multiple things at once, and that can learn, one of the beautiful aspects of deep learning is that we can learn from multiple inputs, so we can try to embed all those inputs into the same perceptual space, and we can try to learn to solve multiple tasks at the same problem. When we think of robots, we also think probably of limitations in terms of the size of the model that we can deploy. This is not a limitation that we normally face when we do image analysis as a standalone process, where we can deploy very large models, and we can be much more redundant in the models that we learn. So this is also an aspect which I'm not an expert on. I admit that it must be taken into consideration. So how can we learn models that can do multiple things and are very compact also?
Thank you. So because it was a very good talk, it deserves questions. So if nobody does it, I keep doing it. So you made this, I like this thing, or you disagree, agree on limitations, etc. So if you can go to that slide, I would like to make you a tricky question.
Okay.
So there are some of those points, for instance, massive amount of training data, prone to overfitting dataset biases, limited expressive power. Do you think these are very specific ConvNet issues, or are they more general to statistical learning? So if I would change SVM, kernel SVM, which when I was young, to ages, glacial ages ago, were the big thing. Would that change very much?
I agree. Many of these issues are related to statistical machine learning in general. With respect to vision, to image interpretation, I would say that compared to previous approaches where we engineered the features, we had the opportunity to build into that engineering a lot of our prior knowledge about the world. So this is an advantage and a disadvantage, because we don't have a very good understanding of, we tend to think of a model of an object as a very schematic process. We are not very able of specifying, for example, how a chair looks like. If this is something that is better learned from data. But if we use, for example, in my field, before deep learning came by, we use features that somehow encoded the properties that we knew were the properties of lesions that we knew were real. So, for example, I know that a cancer that has a stellate pattern, I know that an area of the image that has a certain pattern has a certain likelihood of being cancer. So, in that respect, that doesn't work as well as using convolutional neural network, because we are not as good as detecting, specifying what a good model for a lesion or an object or anything else is. But it was it required a little bit of training data, and people had the impression, not necessarily it was true, that it was a little bit more interpretable. But as a whole, these limitations are limitations of machine learning. It will probably be the same for speech or text, or some of these might be exacerbated by the nature of images that are more memory intensive, but as in general terms, I think they are the same for machine learning, for all machine learning applications.
I would make a distinction between generative approaches and statistical learning approaches. So whenever you go for discriminative methods, and at the end of the day you are modeling only the likelihood and not the posterior, it's data driven, and then a lot of things follow, right?
Yes.
And this works best.
That's true. That's true. Generative models are they are more powerful in many respects. I had to make a choice, and what include and not include. After all, the time is limited, but it is true that some of these properties may not apply to generative discriminative models. Although some of these also apply. For example, you need lots of data. You probably need even more data to learn a very good generative model than you need to learn a very good discriminative model. But others don't necessarily apply. The other thing that the other distinction that we have to make is model over data. So in ConvNets, in convolutional neural networks, the model is relatively simple. It's most of the learning is towards the data. In other approaches, we might have more prior information embedded into the model, the type of functions that the model can learn. That is what I actually mean by expressive power. It's not that they cannot express, is that they have certain assumptions that have been built into ConvNets, and this sometimes limits the type of functions that we can learn from with them. This is what my idea necessarily.
Okay, then thanks, Lia. I think we can close here, and please come back for the next lunch.